Good afternoon, everybody. My name is Rajesh Vaidishwaran. They call me RV, just like the RISC-V. I'm from Netronome. I'm the Director of Engineering and Senior Principal Architect. My background is from software. I'm a software guy at heart, and I've been doing hardware stuff. So I would like to thank, at the outset, Steven Zagorianakis, who's also in the audience here, and Gavin Stark. They co-collaborated with me on this presentation. I hope many of you had the opportunity to hear Steve talk yesterday about building massively parallel systems. This talk and that talk are related very closely because we build massively parallel systems with thousands of RISC cores and make it efficient with a command-driven data transfer protocol. There's been substantial interest in data transfer, and we have heard TileLink multiple times throughout this conference at this point. And there is also C6, and there is OpenCAPI. And in the area of shared storage, there is now Gen Z. What we have found at Netronome is, as we have built a very high performance and massively parallel system, that there is a need for a third kind of protocol, something that, as a programmer, you get to control, and something that can be extended across chip to chip, chiplet to chiplet, and also intra-chip. We also found the need to extend the RISC-V instruction set with our custom instructions so that you can enable this kind of programmer-managed data transfer. The other part that I will touch upon here is transactional memories, which Steve's talk was, he talked more in detail about, and how with our extensions to the RISC-V chipset that we can natively leverage transactional memories. So what is transactional memory? We have the concept of CPUs, and you take work and you give it to the CPU. You take data, you process it inside the core. Transactional memories are where we do it the other way around, where you have data sitting in memory, and we perform operations in proximity to where the data is. So it's very closely coupled. It's hardwired transaction types, things such as atomic transactions, stats updates, CRCs, and even crypto. So the efficiency of moving the data in close proximity to a transactional processing engine is much higher and scales with massively parallel systems. And how do we drive this? So this is the general concept of building massively parallel systems that Steve's talk was about. And this talk, we will just focus on how we drive the data and how we drive the instructions between the cores and the transactional memories. So the idea is that it's command-driven, and you can pass data along with the commands. The commands are very specific, and the commands may or may not need to produce results for you, and we can results that you need to see. We'll have examples of both types. So what is Netronome's instruction-driven switch fabric? So it's a scalable interconnect. It is a flexible fabric that is distributed, and it's programmer managed. It has the ability to transport off-the-shelf interfaces like C6, PCIe. It supports transactional memories natively. And it scales from chip to chip in a chiplet system or island to island inside a die. And I'll talk about what islands mean here. A picture that I've shown here is an NFP, a metronome flow processor, and a couple of data processors hanging off of that inside an MCM. And there is a chip-to-chip connection between two NFPs when the second NFP off of it is hanging an FPGA or a coprocessor. So we show C6 as the interface here. We have coherency, and that's a non-coherent interface to the FPGA. It's a PCIe card. So why is this important? In a system where you have really small, it's a really small chip, it's a really small package, and you have multiple interfaces, it doesn't matter because you have enough pins, you have enough wires that you can put there, and it won't impact the cost of your package, impact the cost of your product. Whereas if you have thousands of cores like we do, and you have to connect to external data processors and external chips, then you really cannot afford the cost of having thousands of wires, millions of wires going across for the different types of interfaces. So you need a shared set of pins, and that's really the only way to scale to very massively parallel systems. A practical implementation of one such system is what we have done. This shows a metronome chip with about 1,000 RISC cores. And we have it organized as islands. And this chip processes network data. It's a network processor in hundreds of gigabits per second. We show that we can be coherent with a host, and you can also expand to processing on a second NFP. The basic data flow here is such that packets come in through the network. We will assign it one of the memory islands. Then a core is given an event saying that there is a packet to be processed, at which point the core takes the packet, as in knows that there is a packet in one of the memory islands to be processed, and issues transactional memory operations, so that if we have to do things like, do I have to change the IP header? Do I have to apply policy on it? Do I have to do L7 deep packet inspection on it? Do I have to do crypto on it? Do I have to discard this packet, send it out to the host, or send it out to the network? Those are all things that need to happen in a 100 gigabits per second system. If you think about it, it's about 3 nanoseconds per 64-byte packet is the amount of time you have. So if you want to do 3 microseconds worth of processing, you'll need something like 1,000 cores. A system like this is connected through an instruction-driven switch fabric. And it allows for you to scale, connect between islands to islands, and you can scale your implementation from small to large fairly nicely. It allows for equal access to memory hierarchies. All types of memories, whether it's DRAM backed memory island backed by a cache, or whether it is access to the host memory over a host interface, or it is just a non-cached transactional memory. And that is the crux of how we build that kind of an efficiency into the system. So how do we manage the data over the instruction-driven switch fabric? So I've shown a subset of the islands that we implement just for illustration purposes. And I've shown the ISF fabric as really two parts. It's really, if you think of it, it's more two virtual parts of a single fabric. And this shows that we have the metronome chip connected to two data processors, one over tile link, one over a proprietary protocol. And on the side, I show what really is happening to one of those processors. Just for illustration purposes, it is set to the side, is we have access to the host's cache, the host's memory through a cache. If you follow the white lines, those are remote cache coherency operations that we can do over the instruction-driven switch fabric. The yellow lines, or the orange lines, show that you can do transactional memory operations over the switch fabric. The reason this works for us, and the reason this generally works, is because the fabric is just agnostic to what is going over it. The endpoints are the ones that get to decide how to interpret what the data is. So today, if it is C6, it's an RFPC island and a data processor. If it's tile link, it's an RFPC island sending tile link over to a data processor over the ISF. And at the endpoints, they get to decide that, yeah, I know I speak only tile link, so what I'm getting is tile link. And we do this with end-to-end credits, that everybody who has a resource keeps track of the credits. Transactional memory operations are handled exactly the same way for us. There is no difference. When we send an operation to be performed, a CRC to be updated, stats to be updated, those things flow exactly the same way through the ISF. And the beauty of that is the programmer-drivenness of this is very important, because in a fabric where multiple entities are connected to each other over it, the person who actually writes the code for it should have the flexibility of actually making it as optimal for their application as possible. I think we heard Dr. Patterson today, and we heard quite a few people talking about domain-specific acceleration. So we don't claim to know what your domain is and what you want to accelerate it for. You know what you're building. The guys who are going to program your chip knows how they want to extract the maximum efficiency out of it. And what we offer is a general fabric that allows both to happen. So in summary, this has been a very exciting time for CPUs in general, with RISC-V doing to CPUs what open source has done in general to software, which is allow lots of people to work on problems and build communities. We believe Metronome's ISF extends that to interfaces. It's practical, it's unified, and it's a general purpose fabric. And as I mentioned before, it's protocol agnostic, and it links endpoints. The endpoints get to decide what the payload is. And where we find it works extremely well with how people want to implement risks is it scales extremely well with chiplets, with MCMs, data processors and network processor communication, and intra-chip interconnects. We have extensions for custom 0 and custom 1 that allow us to combine the power of a RISC-V and transactional memories, so that we can natively leverage transactional memories in the Metronome RISC-V system. We all understand that different interfaces and protocols are needed for different functions, and that's not going to go away. we are not going to solve that problem in any specific way, but we offer a very practical and efficient way to solve that problem by allowing a transport that scales. The example that I talked about that we have implemented is a multi-core high-speed networking system, networking chip, something that processes millions of packets per second. The efficiency of processing a packet and being able to spend 3 to 5 microseconds is something that you can very practically and easily get with 1,000 cores, and very efficient transactional memories is what we've found. So I just wanted to share those thoughts with you guys. You guys should go down and check out the ODSA Alliance. It's the Open Domain Specific Accelerator Alliance that Metronome and a few companies are a part of. And you're welcome to join us and work with us. This is really an alliance that we're building to leverage work in the community so that we can all work together. Metronome's ISF is available there in some form. And if we want to further this conversation, we can take it outside there. So that's all I have for today. Thank you for listening.